We have seen the exclusive OR gate before. This is the look of the exclusive OR. It has two inputs A, B. The output is written this way, and this is equal to A, B bar ORed with A bar, B. And this is equal to this truth table, which is equal to M1 ORed M2, two minterms M1 and M. Now this is called the odd function. A exclusive OR B exclusive OR C is equal to this. This one here, ANDed with the C bar, ORed with this here, complemented, ANDed with C. And this is equal to this. If we take the exclusive OR, we expand it. It is A B bar, ORed with A bar B, ANDed with C. Here is the exclusive NOR. It's AB ORed with A bar, B bar, the whole thing ANDed with C. And this is equal to these terms, and these are the minterms M1, M2, M4, and M7. This is the exclusive OR 3-input gate. Notice the minterms here. This is M1, M2, M4, and M7. If you try to simplify this map, you will end up with 4 terms, with 4 minterms. You cannot simplify it. Now this is the truth table for this circuit. Okay, here it's equal to 1. It's the odd function. It counts the number of ones at the input. Here the number of ones are odd, so it gives me a 1. Here the number of ones at the input are odd. It gives me a 1. The same thing goes here and here. Now the exclusive NOR gate is an exclusive with OR with an inverter at the end. So it is equal to this at the output. A exclusive OR B, and then there is this complement. This here results in this. It's A, B, ORed with A bar, B bar. Okay, which are the minterms 0 and 3. It is the complement of the exclusive OR. It is called the even function. This is a 3-input exclusive NOR. This is equal to this, ANDed with this, ORed with the complement of this, ANDed with the complement of C, which is this. If we expand this one here, we get this term. If we expand this one here, we get AB ORed with A bar, B bar, the whole thing ANDed with C. And these are the minterms 0, 3, 5, and 6 here on this map. Again, you cannot group the minterms with any other minterms. And this is the truth table. Notice, this is equal to 1 to say that the number of ones at the input are even. This is equal to 1 to say the number of ones here are even. The number of ones here are even. The number of ones here are even. So this is called the even function. So you notice that they are the opposite of each other. This is the odd function. These are the minterms here and here and here and here. While the even function are with the other cells. The one is here instead of this. Okay, here it's 0, while here it's 1. And this is a minterm, and this is a minterm, and this is a minterm. The same thing for variable odd even functions. This is the odd function for a 4 variable, and this is the even function for a 4 variable. Notice that they are the complement of each other. This one here is the complement of this. Now, what do we need the exclusive OR gate for? Okay, we can have something called the parity generator and the parity checker. Okay, data is transmitted from point A to point B. Okay, there is a bit called the parity bit that we generate to send with the original data in order to have a check. on the validity of data if there is a single error on the data. Okay, even parity generator. Suppose we want to transmit the data XYZ from point A to point B. This is the data that is to be transmitted. We can agree with the receiver at the other end that we will send along with the data something called a parity bit to make sure that nothing happened to the original data on the way. Okay, if we talk about even parity, then we want a circuit to send a 0 if this data is transmitted, and we want a circuit to send a 1 if this data is transmitted, and so on. You will notice that this is an exclusive OR gate. These are the inputs to it, X, Y, Z, and this is the P, the output of the parity. This is the parity bit. So all these 4 bits are transmitted from point A to point B. Now at point B, at the receiver, he will receive these 4 bits, X, Y, Z, and P. Okay, and these are all the different combinations of these 4 bits that might be received at the receiver. Okay, and here we have something called the parity checker. Okay, now in this case, if we're talking about even parity, we say that this data has no fault on it because it has an even number of ones. So the C output of the circuit is equal to 0. However, if we receive this, that means something has happened wrong in one bit. So we have to flag the error here by setting the output C to 1. And this here, we received an odd number of ones, so this is wrong. This is correct, this is wrong, this is correct, this is correct, and so on. Now, the circuit that represents this truth table actually is an exclusive OR that has the 4 inputs here, X, Y, Z, and P, and this is the check bit here at the output. So this is a parity generator, and this is a parity checker.